In the last lecture, we discussed implementation of critical section with the support of hardware instructions. At the fag end, we introduced semaphores. Now, dictionary meaning of semaphore is signaling. It had a special connotation of sending messages with the help of two flags by the Navy personnel. Since semaphore is an extremely important concept, let us resume our discussion today by giving the definition of semaphore once more. Here is the definition of the semaphore, that S, which is called a semaphore, is an integer, it's a variable. Two functions have been defined on it. One is wait S, another is signal S. Wait is defined as that while S less than equal to 0, do no operation. Okay, that means it's busy waits here, and therefore the process busy waits here, and therefore sometimes it's called a spin lock. Okay, and S, if it comes out of this while loop, that means S is equal to 0. Sorry, S less than equal to 0. That means if S is greater than 0, only then if S is greater than 0, only that it comes out of this wait loop, then S is decremented, right, and the process can go ahead. In the case of a signal S, the value of S is incremented. Okay, the previous names of wait S and signal S are PS and VS, and therefore these two names are also used. One important aspect of these wait S and signal S operations are this, that they are atomic operations. They have to be implemented as atomic operations. By that, it's meant that once that execution of wait S starts, okay, till S is decremented, that operation, that means the execution of this function, cannot be discontinued, okay, cannot be preempted. Similarly, in the case of a signal S, the incrementation S to S plus 1 cannot be preempted when this is being incremented, right? Therefore, both wait S and signal S is important to note that has to be implemented as an atomic operation. Now let us see that how these two operations on the semaphore can achieve mutual exclusion. As we said earlier, suppose that there are several processes, P0 to Pk, are competing to enter the critical section. Okay. Now, one of them, say Pi, will be able to make let us assume that initial value of mutex, the semaphore here, that mutex is equal to 1. Then one of the processes, say Pi, right, will find the value to be 1, will then enter you'll find the value to be 1 here, right, and therefore will come to this next operations, which is decrementing S, right. Therefore, it will decrement the value to be 0. It was 1, it is decremented to 0, and then it just enters the critical section. All other processes, starting from P0 to Pi minus 1 to Pi plus 1 to Pk, will now find the value to be 0, and therefore it will spin lock here. Okay. Now, when the process Pi, after execution of the critical section, okay, wants to come out, then it will execute the signal mutex. The exit section will be executed, which is signal mutex. Then it will increment the value of to 1, and it will enter the remainder section. Now, the other processes which were waiting or spin locking on S, right, one of them will find now the value to be equal to 1, and therefore it will decrement the value to 0 and will enter it. Okay. Therefore, one of the other waiting processes now can enter the critical section, okay, but all the remaining one will still spin lock at this point, okay, at the wait mutex. That way, that mutual exclusion is achieved by means of the semaphore. Now, there is another application, let me tell you, of the semaphore. Here we are using the semaphore, that variable sync, right, to synchronize between two processes P1 and P2. Here the initial value sync has been kept as 0. What is intended is that P2 will not move beyond this point before P1 reaches this point. Okay. That is why that initial value of sync has been kept to 0. That if P2 reaches this wait sync before P1 reaches signal, then P2 will spin lock here. Right? It will find the value to be 0, will spin lock here. On P1 reaching the signal, okay, point, then it will make signal sync. Therefore, sync value will be incremented to 1, and then P2 can proceed from this point onwards, right? But however, if P1 reaches this signal point earlier than P2, then P1 has already incremented the value from 0 to 1, and therefore P2 will just check the value of sync and then can go ahead with the execution of the remainder portions of P2, which is P22. Okay. Therefore, you see that semaphore can be used, okay, either for mutual exclusion or for synchronization, depending upon how you use the wait and signal mechanisms and what is the initial value of the semaphore variable. Right. Now, as I said, that when a process executes wait, and if it finds that the value of the semaphore is less than or equal to 0, it spin locks. This is essentially the wastage of processor time, because it's busy waiting and it's doing nothing. No useful work is being done, and therefore the processor time is wasted. Now, it has an advantage, okay, if in a multiprocessor system, the semaphore which has been put to less than equal to 0 by a process or a thread, okay, is running in another processor, and if the time of execution of that process or the thread, that means within the critical section, is not long enough, then it is advantageous in the sense that this process will wait for few instructions, possibly only, and then can enter its critical section. Okay. The alternative is that this process, which is waiting on that semaphore, can be put to sleep till the other process exits the critical section. Right. Now, that should be done when the wait time is too long. If the wait time is short, in that case, that putting that process into a sleep state essentially involves that status of all the registers, etc. That means the switching from the running state to the sleeping state, all the status information that has to be saved are to be done, which is also a time consuming and which is also an overhead on the processor. And therefore, if the wait time is small, then the process may spin lock, but if the wait time is too long, then naturally it is advantageous to put the process to sleep. But for that, we'll have to redefine semaphore, and let us give the redefinitions of the semaphore. Here we have redefined the semaphore. Here, semaphore has been declared as a type. It's of record type. Okay. The record has two components. One is a value, another is a list of processes L. Okay. Let us see. This is the semaphore type. Okay. It has two components. One is value part, and there is a list of process part, that means L. Here, a list of process, that means their PCBs, can be kept. A list of process can be attached here as L. Okay, it's kept as a linked list. Now let us see that what's the weight and signal definitions we give on this semaphore tie. Let S be a variable of type semaphore. Here weight S has been defined that value part of S, that means S dot value is decremented, okay, by 1. Now if it is found that S dot value is less than 0, then this process is added to S dot L and it calls a system call to block itself. That means it goes to the sleep state. Right. Say for example, here that if it finds this process, a process P, on executing wait S, if it finds that the value of this semaphore is say -3, then it will make it -4 by executing this instruction, and since that S dot value is less than 0, this process will be added to S dot L. Therefore, so this process now will be added to S dot L, and this process P will block itself. That means it will go to a sleeping state. Okay, it will be no more executing. Now let us see what the corresponding signals operation is. The signals S operation increments the value part of it. That means S dot value is incremented, and if it finds that S dot value is still less than or equal to 0, then one of the process, say P, will be removed from this list L, and that process will be woken up by calling the system call wake up P. Now say here the situation is that if this process executes that signal S, it will find a value to be -4, value part to be -4. Then so one of the process, say this one, will be removed from this list. Okay, let this process be P, and then it will be sent into the ready. Okay, it will be sent into the ready queue. That is what has been shown over to here. That remove a process P from S dot L. So this process is removed from S dot L, and wake up P essentially that it will be sent to the ready queue, which will be dispatched to the processor. Okay, when the scheduling algorithm decides that P can be put to the processor. Right. That is what is the meaning of signal S. Okay, and you see when it's done that S dot value has been incremented by 1, therefore S dot value will be incremented by 1. It will be -3. Now you see that depending upon the initial value of this value part, this number may indicate the number of processes that is still linked up in this S dot L. Okay, that means the number of processes that is waiting with the waiting at the semaphore S. Okay. Now this is our therefore the semaphore redefined. That we define the semaphore, repeating once more, that as a record, the value part and a list of process part. Weight is decrements it, and if the value is found to be less than 0, then it's blocked. Okay. Added to the list, and the signal is it's incremented, and if the value is found to be still less than or equal to 0, then one process is removed and that process is sent to the ready state. Okay. Now important thing is this both weight S and signal S has to be implemented as an atomic operation, right? And to implement it as an atomic operation, now we can take help of, right, that in the case of a single processor system, we can disable all interrupts when that wait S and signal S is being executed. And in the case of a multiprocessor system, then either you can use a software solution we discussed earlier, or you can use special hardware instruction to implement it as an atomic operation. Now, for the important point is this, that both weightage and signalage has to be implemented as an atomic operation. Now, another aspect is this. One thing is that it is pretty obvious that if we execute that weightage or implement weightage and signalage as an atomic operation, mutual exclusion will be achieved, right? But the bounded operation that we can achieve by ensuring that the Q is maintained as a FIFO Q. That means the Q that we are talking about here, this Q, if you implement it as a first in, first out list, okay, then whichever the process that came in first, okay, will be removed from this list, and therefore you see that we can achieve this bounded weighting, that the process need not be or will not be in this linked list, okay, in the waiting state, okay, indefinitely. Now, the semaphore that way being redefined, let us now apply this semaphore, redefined semaphore, on few classical problems. Now, these classical problems are in fact very representative problems, okay, and most of that semaphore, that primitives that are defined are applied on these classical problems to check their validity. Now, one of the classical problems that we'll be discussing is that bounded buffer problem, which you are familiar with already, right? Now, see this bounded buffer problem, there is a producer process and a consumer process, as we know, right? The producer process is producing an item here in next P. We are utilizing here three semaphores. One is an empty, one is mutex, right? Another is full. That mutex semaphore is initialized to 1, empty semaphore has been initialized to n, and the full semaphore has been initialized to 0. Okay. Now, why so? Let's say that to start with, the mutex is initialized to 1 just to have this critical section, right, of adding an element to the buffer, okay, or removing an element from the buffer. Therefore, you see that wait mutex and signal mutex, and here wait mutex and signal mutex, this semaphore has been used to achieve the mutual exclusion of this portion with this portion between producers and consumers. Let me tell you here that though we are talking, I mean, as if only one producer process has been shown and one consumer process has been shown, in practice there may be more than one producer process and more than one consumer process. There may, right? And therefore, all of them will be utilizing that mutex semaphore to have a mutual exclusion. That empty semaphore n initial value represents that all the buffer which is of size n are empty, right? And the full indicates that none of the buffer position is occupied, okay? It has been filled up. Now let's see the producer process. It produces an item in next P, then it's wait on empty, right? That means if it's found that there is no empty space, then naturally it has to wait, okay? And it has to wait means in terms of our redefined semaphore operations, it has to go to sleep. To be waked up, okay? It will wake up on signal empty, right? Now here wait empty, then this is the critical section where the next P that has been generated is put into the buffer, then signal mutex, and then here signal full. Signal full is this, that if a consumer process is waiting because there is no item in the buffer, then the consumer process should be woken up, okay, and the consumer process can start, right? Here let us see the consumer process. The consumer process first waits on full to be signaled by the producer. That means if there is no item, then the consumer process waits here to be signaled by means of the producer process, right? And if it is sleeping, then it will come out of the sleep and then can enter the critical section, right? In the critical section, it removes an item from the buffer to next C, then it signals mutex, and then it signals empty. This signal is to any producer process which was waiting on that semaphore empty. Therefore, you see essentially that empty semaphore and the full semaphore are used to synchronize the producer process and the consumer process on that buffer empty and the buffer full situation. In the case of a buffer empty, the producer process waits to be signaled by the consumer process. Okay, you see. And in the case of a buffer full, consumer waits on full. That means if the full situation is 0, that means if there is no element here in the buffer, the consumer waits to be signaled by the producer process. This way, a cooperation and synchronization is achieved between the producer and the consumer, right? Now, this is a good example of a problem where the semaphores can be used, okay, very fruitfully and effectively to solve the problem, right? Now, let us come to another problem, which is that we call the readers-writers problem. Let us see what this readers-writers problem is. That in the case of a readers-writer problem, as if there is a board, okay, the board is represented, implemented in the form of a file. There are some readers and there are some writers. The readers can read from the file whatever has been written can be, the readers can read from it, and the writer can write into the file. That means the writers can write on the board. Now the situation is that when writer is writing it, naturally no reader or no other writer should be able to access the board. Okay, and here we give the readers the priority. That means if a reader is reading it, right, then any number of readers can enter into the file and read it. That means any number of readers can start reading from the board. Okay, but once a writer starts writing it, that means is allowed to enter the writing state, okay, on the board, then naturally no reader can read from it. Okay, no reader should be allowed to read from it. Neither any writer should be able to write on it. Okay, therefore it has to be exclusively to be given to the writer. Okay, this is that has been pointed out here, that in the case of the readers-writers problem, any number of readers may simultaneously read from the file. Readers have priority. That means when there is at least one reader reading, subsequent readers need not wait, and only one writer at a time may write. And if a writer is writing, no reader may read it. Okay, this is the 4 conditions that have to be satisfied, and let us see that how we can realize it by means of the semaphore. Now, one thing that I have forgotten to mention, that when I am redefining the semaphore, and the semaphore value can have any integer values as have been assumed over here, as I'm done over to here, such semaphores are called counting semaphores, okay, because that value can be utilized as to the number of processes that is still waiting, okay, at that semaphore, right? Therefore, we call such a semaphore a counting semaphore. Now, here's we see that how the readers-writers problem is solved by means of the counting semaphore. Here once more we have kept a mutex. that one semaphore is mutex, which is initialized to 1, right? And this semaphore is utilized to achieve the mutual exclusion of the critical section. Here it is a critical section. This mutex is utilized to achieve that mutual exclusion, right? Now here another semaphore has been used. We call that WSEM or right semaphore, WSEM, which is also initialized to 1, right? And another integer variable has been kept, which is reader count, right? This is a reader count, is a number of readers that is right at this moment is reading from the file, okay, reading from the board. The reader count is initialized to 0. Therefore, we have two semaphores, which is one is mutex, another is WSEM, and another integer variable which keeps count of the number of readers. Now here is a reader process that has been defined, and here is a writer process that has been defined. Okay, let us see the writer process first. It waits on WSEM, right? WSEM initial value is 1. Therefore, if someone has entered the critical section with respect to WSEM, right, then the writer has to wait. Okay, and it signals WSEM. That means when it comes out of the critical section, then it signals WSEM. Here is the critical sections which the writer is doing, that means perform writing. The reader section is like this. This is a critical section, right? The reader count is incremented to reader count plus 1. First it waits on mutex, right? If the original value is 1, right, therefore the first one can enter it, reader count is incremented, and if the reader count is equal to 1, right, then it waits on WSEM. Now it waits on WSEM, I am explaining it out. Now if the reader count is not equal to 1, then naturally it signal mutex and it can perform reading. Now assume that there is one reader here. One reader here means that reader count, that first reader that entered over to here, the reader count was 0. The first reader that entered has incremented the reader count to 1. Since it found the reader count equal to 1, then it will wait on WSEM. Now if any writer is here, naturally the first reader has to wait on WSEM, that means has to go to sleep, right? It will be awakened from the sleeping state by means of signal WSEM. That means when this writer comes out of the perform writing, that critical section. Okay. Now let us assume initially that there is no writer. Therefore, the first reader has entered, has executed wait WSEM, executed signal mutex, and has entered the critical section. The other readers, okay, that will, I mean, since it has executed signal mutex, the other reader simply will wait mutex, increment the reader count, and then come out of the signal mutex. Therefore, once entered, can enter the perform reading. Therefore, once a reader is here, any number of reader now can come into it. As the readers comes into it, the reader count is incremented by 1. Okay. Now, as a reading is performed, okay, as a reader has done reading, performed reading operation, okay, then it can come out of the reading of that critical section. Once more, it is wait on mutex. This is a critical section, right? The reader count is decremented, and if it found that reader count is equal to 0, then it only signals mutex. That means, so for example, 10 readers has entered into it. Okay, each one of them, as it's coming out one after the other of these reading operations, okay, we will decrement the reader count one after the other. The last one of them that is coming out of this reading operation, okay, will signal WSEM, right? Now, as the last reader signals WSEM, any writer that is waiting here, okay, can enter its critical section, okay, and starts writing, perform writing. Now, as long as the writer is performing writing, no other process, either the writer process or the reader process, can enter its critical section. Let's see why. So naturally, all other writers will wait here. WCM's initial value is 1. Okay. Therefore, as per the definition of wait is, the tested value has been decremented to 0, right? Okay. And since the tested value is 0, right, for the first writer, it will enter the critical section. Okay. I mean, state value is not equal to, is equal to 0, and therefore this will be skipped and the first writer will enter the critical section. But any other writer will decrement the value by -1 and will find therefore the tested value to be negative and therefore will be waiting here. Therefore, any other writer that will try to enter this perform writing critical section, so it wait here. Let us see what about happens to the readers. The reader that wants to enter, first reader that wants to enter, after a writer has entered into the critical section, will increment the read count, it will wait mutex, will increment the reader count, right? It will find that reader count is equal to 1, 0, and therefore reader count will be made equal to 1. And since it's a fast writer, the reader count equal to 1, it will also wait on WSEM. Therefore, the fast reader that wants to enter perform reading critical section will wait on WSEM. All the writers will wait on WSEM. All the other readers will wait on mutex. Because the fast reader is now waiting on WSEM, it could not come out of WSEM and therefore could not signal mutex, and therefore all other readers will be waiting on wait mutex, right? Let me repeat what happens, that if a reader is here in this critical section, all writers are waiting here on WSEM. The first reader that wants to enter after a writer has entered its critical section will be waiting on WSEM, and all other readers will be waiting on mutex, right? Now let us see what happens when this writer comes out of this critical section by executing the signal WSEM. And as soon as signal WSEM is executed, right, this writer comes out of it, either one of the writers here or the first reader here that can be put to the ready state, okay, that can be now awakened, and the writer may now come into the perform writing operations, or the reader may be allowed into the perform reading operations. Now remember one thing, that if a reader is allowed into perform reading operation, all other readers can come into it, which is waiting over here. Now this is a policy decision, a scheduling policy decision the system has to take. Whether one has to want to give the priority to the reader, or one wants to give the priority to the writer. If the priority to the writer has to be given, then a process has to be taken from here and has to be awakened. If the priority has to be given to the reader, then a process has to be taken out of the first process that is waiting here, has to be taken out of this queue and have to be given the permission to enter into the reading operation. Right. This is the classical reader and writer problem. This also represents a whole lot of, I should say, that representative problem for a whole lot of similar problems like that. Okay, and as I said, that any semaphore primitives or any I should say that synchronization primitives that are proposed are these classical problems are used to check their validity. Okay. So the last problem that now I come to is called the dining philosopher problem. Right. Here is the dining philosopher problem, once more a very classical problem. Right here we have 5 philosophers, right? So P0, P1, P2, P3 and P4. These are the 5 philosophers. Now sitting around a round table, right? The philosophers spend their time by thinking throughout their life, and when they find hungry, what they do is that they first pick up the left fork, okay, then he or she picks up the right fork, and whatever food is there, say some spaghetti is there, okay, he eats from there. After his hunger is over, that means he's satisfied, he puts down his right fork and then he puts down his left fork and starts thinking once more. Okay. Now let us forget the, I should say that problem of cleanliness. The situation is that there is only 5 forks once more. The forks are F0, F1, F2, F3 and F4. Any philosopher that wants to eat, right? Say for example, this philosopher, he wants to eat. The philosopher has to pick up the left fork, then has to pick up the right fork and then eat, and then we will put down the right fork and then we'll put down the left fork and start thinking once more. Okay. Now, important thing over here is this, that when a philosopher feels hungry, he should be, or he or she should have the availability of both the forks. That means he has to have the left fork as well as he has to have the right fork. Okay. He picks up the left fork, then he picks up the right fork, and then he eats from the plate, and then he puts down the right fork, and then he puts down the left fork and starts thinking once more. Now, such a solution of such a problem has been proposed here. Here, the fork has been declared as an array of semaphores, okay, that initial values are all equal to 1. Array 0, 1, 2, 3, 4 of semaphores, right? 5 forks are there. Here is the philosopher process, right? Repeat until false, that means to repeat indefinitely. The philosopher thinks, right? Now when he feels hungry, right, it waits on fork I. That means if the fork I is busy, that means it has been taken over by another philosopher who is sitting possibly at his left or at his right, then it has to wait. Okay. That if it does not have to wait here, that means the philosopher can get the fork I, then he attempts fork I plus 1, which is on the right hand side of the philosopher. Now this mod 5 is to take care of that circular, say, positioning of the forks, right? Then he waits on fork I plus 1 mod 5. For example, say this philosopher. The philosopher will try to pick up this fork. If it finds that this fork is occupied, then he has to wait. When it can grab this fork, then it will try to pick up this fork. And if the fork is occupied or taken over by P0, then this philosopher has to wait. Once the P0 releases it, then P4 can get this fork. Now, P4 has both the fork F4 and F0, and therefore the philosopher P4 can start eating, right? That is the position that has been depicted here, that it waits on fork I, then it waits on fork I plus 1, and if it can come out of both these waits, then it eats. After eating, it signals fork I plus 1, that means it releases fork I plus 1, then it signals fork I, it releases fork I, okay, and then goes back and starts thinking once more, okay. Therefore, that's the situation that the philosophers are spending their lifetime thinking and eating alternatively, okay. Now, try to see the situation, what happens, right? Say, here is a philosopher, okay, some philosopher, say P0, right? Now, assume that since P0, P1, P2, P3, and P4, all of them are concurrent processes, the situation may turn out to be that all P0, P1, P2, P3, and P4, okay, right, executes this wait for chi instruction simultaneously. That means P0 picks up F0, P1 picks up F1, P2 picks up F2, P3 picks up F3, and P4 picks up F4. All the philosophers have picked up their left fork. Okay. Now they are now trying to get their right fork. Okay, and all of them now waiting for the right fork. Situation is that all of them have got the left fork, and all of them are waiting for the right fork. And you know, it's a very undistinguished postures. The brilliant philosophers will be waiting for the other philosopher to release the fork, and therefore will be in a deadlock situation and will possibly starve to death, right? Therefore, this is a situation which we call the deadlock situation. In the case of a deadlock situation, each of these philosophers has got one fork, one resource, and is waiting for the other resource to be available to go ahead with the computations, with the process. Okay. Now, such a situation, we call it a deadlock situation, and therefore something has to be done so that these just deadlock situations can be remedied. Okay. There are several solutions of it. One is that allow at most 4 philosophers. One important thing that you should realize here, that even if, okay, in this situation, right, even if one philosopher is not trying or has not grabbed his left fork, the other philosopher can finish eating. For example, say this philosopher has grabbed his left fork, okay, and is waiting for the right fork, right? But since, say that philosopher P0, assume that, accept philosopher P0, the philosopher P1, P2, P3, and P4, all of them have simultaneously executed wait for chi, right? In that case, and the P0 is only philosopher which has not done it. In that case, say P1 has picked up F1, P2 F2, P3 has picked up F3, and P4 has picked up F4, then P4 can get F0, okay, and therefore it can finish eating, release F4, which P3 can now pick up, then release F4 and F3, P2 can now pick up F3, release F3 and F2, and then P1 can pick up F2 and eat and release F1 and F2. Therefore, as long as only 4 philosophers are allowed to execute this wait instruction, okay, in that case, that there is the possibility of the deadlock vanishes, right? Now, this is one of the solution that we can attempt. That means we allow at most 4 philosophers to be it. For that, what we do is that we put this table into a room, and at any instant of time allow only 4 philosophers to enter. This can be achieved by means of, what I say is that we declare, say, room to be a semaphore once more with an initial value of 4, right? And we put wait room here and another call signal room here. Now the situation is this. You can see that since the initial value of the semaphore is 4, right, then 4 philosophers at most will be allowed to pass through this wait statement. The 5th philosopher will wait here and therefore will be put to the sleep state, right. In that case, the other 4 philosophers can complete ultimately all of them the TET operations, and as a philosopher comes out of the signal, it then signals room so that any philosopher that is waiting here can now enter the room. Okay. Therefore, by just allowing 4 philosophers to enter the room and share the table, we can solve this deadlock problem. Now, you can see that essentially the deadlock problem is that all the processes have got a resource and will be waiting for other resources which have been attached by other processes. Okay, and the situation is such that if the other process does not release that resource, this process cannot continue. Since this is the situation, no process can continue with its job and comes to a deadlock situation. This, therefore, in the case of these operating systems, these deadlock situations under such circumstances may arise many a times, and therefore the deadlock situation is a topic which needs special attention, and we'll talk about the deadlock situations in our subsequent lectures. But before that, let us see what can be the other solutions of these dining philosopher problems. One is that, as I said, that allow at most 4 philosophers. The second solutions may be allow a philosopher to pick up forks only if both are available, right? If that be the situation, that allow a philosopher to pick up forks if both are available, and if it has picked up, if the philosopher has picked up only one fork and the other is not available, then he should release it immediately. Okay, right. Another solutions may be, which is called the asymmetric solution. In this case, that odd philosopher leaves the left fork first, and even philosopher tries to leave the right fork first. In that situation, you see, you can try to satisfy yourself that the deadlock situations will not happen. Right? Therefore, we have given 3 possible solutions of the deadlock situations in the case of a dining philosopher problem. One is that restrict the number of philosophers. Second is that allow the philosophers to pick both the forks. If both the forks are not available, he should relinquish the fork he has picked up. And the third is an asymmetric solution. Now, as I said, that deadlock is a topic which needs special mention, and in our subsequent lectures, we'll talk about deadlocks. That's all for today's lecture.